Hi, cloud practitioners. Today I want to talk about distributed sagas with AWS Step Functions. We're going to learn why sagas solve consistency in microservices, how to orchestrate them with Spring Boot and Step Functions, and implementing compensations and error flows. So first we have to understand the limits of two-phase commits. And so a two-phase commit is a protocol used in distributed systems that ensures a transaction is either committed, that's successfully completed, or aborted, rolled back across multiple services or databases. So phase one is the prepare, and phase two is the commit or abort. So the limitations here is that the coordinator is a single point of failure, and that blocking and recovery are challenges, scalability problems, and there's a lack of fault tolerance as well. The Saga pattern solves a two-phase commit problems by having no single point of failure. It's non-blocking, it's scalable, and it's fault-tolerant with compensating transactions. And isolation is really important because it has a separation of concerns, this independence and autonomy. It's the failure is contained, and there's these. It's achieved by having service boundaries, separate code bases, and a distributed deployment. So, what is a Saga pattern? It manages long-running distributed transactions by splitting up into smaller, isolated steps with compensations for failures. So it can be done with choreography, where each service independently handles its part and triggers the next service without a central coordinator, or it could be with orchestration, where there's a central coordinator, like in AWS Step Functions. So we'll use a real-world scenario here, where there's an order service, an inventory service, and a payment service. So the customer places an order, triggering the order service to create a new order in the system, and then the inventory service is triggered where it checks for stock levels, reserves the item, and updates inventory to reflect the order. And then the payment service is called, and it processes the payment, and if it's successful, the order is confirmed and finalized. And then we have our failure scenario, the compensations. So if the inventory service fails, the order service will cancel the order. And if the payment service fails, then the inventory service will roll back the stock reservation, and the order service will cancel the order. So we've got microservice isolation and independent data stores. With the isolation, each microservice handles a single domain, ensuring clear separation and scalability. And with the independent data stores, each service owns its own data store, promoting decoupling and independent evolution. So with the isolation of microservices, you can have microservices that are written in any language, and they can scale up and down as needed. And with the data stores, you could use any kind of database you want for any service. And different teams could work on different microservices, and they could be deployed separately as well. So here's a look at the system architecture. The user hits an API endpoint to trigger the AWS Step Functions workflow. The first state is the place order state, which hits the order service and its own data store to create an order. Then the check inventory state triggers the inventory service to reserve inventory. And then accept payment uses the payment service to accept the payment. If the payment is rejected, then the inventory is released and the order is canceled. So let's talk about building the Spring Boot microservices. You want to create order, inventory, and payment services with JPI and REST. And you want to expose compensation endpoints, cancel, and release. So here's a code snippet for the REST controller mapping for orders, for creating an order. Pretty straightforward. And then this is the code snippet for the REST controller for canceling an order, where the ID is taken as a parameter. So we'll want to also define the state machine itself and author Amazon States language, ASL, JSON, and they use choice states for business results. So here's a look at the ASL JSON. It starts with the order service, which is a type of task. It invokes the order service Lambda. And then if there's an error, it fails the Saga. Otherwise, it moves on to the next task, which is the inventory service task. And here's what our state machine looks like. It starts with the order service. Then there's the inventory service. the check inventory choice state. And if that fails with a 404, there's a cancel order compensation and the Saga fails. Or there's also the payment service, the check payment choice state, and then release inventory and cancel order compensations. So let's talk about compensation and error handling. We're going to implement compensating actions in the microservices. The check inventory choice transitions to cancel order of inventory service returns a 404. And the check payment choice transitions to release inventory if 402 is observed from the payment service. This is what the release inventory compensation looks like. There's the order ID, the items, and the release quantity. And the cancel order compensation is just the order ID that's posted to cancel in the order service. And here's a look at what the approved payment step function flow looks like. Where the Saga is completed right after we check payment. And then here's what the insufficient inventory flow looks like, where the check inventory choice invokes cancel order compensation and the Saga fails. And finally, the failed payment flow, where the release inventory is triggered and the cancel order compensation is triggered. I also instrumented the code so that X-ray tracing is enabled. You can see what every single invocation time looks like for the state machine itself. You can see it's 2.97 seconds. The inventory service function took 3 milliseconds, and so on. You can break down and find out which are your worst performing tasks as well that need maybe be tuned, or a database needs to be changed. Database query needs to be changed. Let's take a look at this in action. So we've got an order with items, product ID, and quantity. And we're going to post to the API gateway. Okay, so we can see we get a response back from the AWS Step Functions. When we go to the state machine, look, oh, and it's exceeded. So let's look at this is got an order service, inventory service, check inventory, payment, check payment, complete Saga. All right, let's see if we can get something. Every third time I've set it up so this fails, so maybe we can get a payment failure. So we'll do another order, and now we have a failure. And so this is the payment service failing. Yes, so we have the order service, state input. We can see here what I put through in Postman, and the response here is a 201 created. It's great. So we go to the inventory service. We have this order ID coming through, and then we have the 201, and then out comes the available quantity and desired quantity on the payment service, which returns a 402, right? So that's payment required, is that status code. So because of that, check payment sees that 402 coming as the input, and then it passes on the order to release inventory, and the inventory is released, cancel order, finally fail Saga. So, all right, so that's the order system in action here. And if you're interested in downloading this, trying out for yourself, you can go to my GitHub where I explain the architecture, how to run it locally, how to set it up, and you can make any changes to you if you want to, and use it in your own organization as a starter. Okay, great, thanks. Key takeaways are that Sagas are used for data consistency without locks. There's a clear separation. There's a choice for business and a catch for errors. And there's two terminal states, a succeed or fail, like we saw before. And you do want to use idempotent compensations Compensations that every time you invoke them, they have the same result. And you don't use exceptions for expected flows. If you're interested in reading further, there's Designing Data-Intensive Applications by Martin Kleppman. And you can download the source at my GitHub as well. If you found this helpful, feel free to like or subscribe as well. Thanks.